in love with my science and math ties. Doesn't get better than that when you have a black hole tie. It's my black hole one. Yeah. Oh, this is not the right folder. I need to go get you guys some work now.
So 10.3 is due Wednesday. 10.4 is due Monday. Right. We'll finish it today. Yeah.
Growing up when I was a little kid, my parents were very poor immigrants to this country, and sometimes I'd be able to go to the library and I would read books on black holes, and I would just be sitting in the library crying, just tears in my eyes, like getting water all over the pages, because I thought it was so beautiful that such incredible objects could exist in our universe, and I just wanted to understand how do they work. I'm very fond of black holes.
And I said, I don't dance. And so I read a biology book. I read a ninth grade biology book. And I was actually thinking, like, oh, this is so cool.
Here it is. There you go. And I believe I posted the solutions to this online. Is that true? The fellas are watching from home. Feel free to type into the chat. If you have any questions, guys, I have the chat up, so let me know if you guys have any questions.
Can I just say getting a huge number on number 5 scared me.
Number 5.
It was like 7 million.
I don't remember that. Oh, was that the Icelandic hunter?
Yeah.
Yeah, the Icelandic hunter must, he must, take his gym time seriously. Maybe that's why he could generate so much force on that sled. But anyways. Yeah, but I mean, it is what it is. The problem gives you those parameters. You must calculate the quantities, and that's that. Whether the numbers scare you or not, don't matter. They don't matter. All that matters is what is it saying. So I believe for 10.4, I have not posted problems yet. Okay, so I'll do that immediately. I'm actually going to leave 10.4 as it is, and we're going to assign some problems based off of it. We don't really have time to derive Kepler's laws, and that is an unfortunate statement because they are very beautiful and very important historically to humanity. So, but I'm going to have to go over some parametric surfaces, 10.5. Oh, and guys, I'm passing out the exams, so since you guys aren't here, I'm gonna have to give them to you when I see you. Or if you can't wait to see them, you can stop by and pick them up from my office. Up to you. I may or may not be there, so. I may or may not be there. Okay, let's try this. Okay, we're in 10.5. Okay, so this is where this class starts to take it up a notch. Each section, it just takes it up a notch. And each section, everything gets cooler. Okay, so you know how we have a vector function? We used to have a vector function R of t. And it was parameterized by some f of t, p of t, and some h of t. Okay, well, now we can have some r or some u v. Okay. Where u and v are similar to t. They're just parameters. T was a parameter. U and v are parameters. There's just more than one parameter now. Before you had just one parameter t. Now you have more than one parameter. So now the book says, okay, call this x of u of v, y of u of v, z of u of v. Okay. What do each of those mean? Okay, well, for example, x of uv, no, it could equal u squared plus 2uv plus v squared. For example, where are you plugging values for u and v, and there will be an output. So let's say I plug in 0 for u and 1 for v, my output would be 1. Okay? It's just a multivariable function now. Okay? So this creates a parametric surface. Surface. Whereas this, with one parameter, created what? A parametric curve. What's the difference between a surface and a curve? Surface and a curve. What's the difference? Yeah. So a surface is a two-dimensional object embedded in three dimensions, R3. And a curve is a one-dimensional object embedded in 3 dimensions, R3. But notice that adding another parameter took our curve to a surface. It's analogous to if this is a length u, okay? Actually, let's say this is length t. And this is length u and length v. This can only generate a length, but this will generate, when you multiply them together, an area. That's exactly what's happening. 2 parameters gives you 2 pieces of information simultaneously. So just like how an element in R2 has an x and a y coordinate pair, and an element in R1 just has an x, adding an extra parameter makes you go into 2-dimensional mathematics. So let's identify and sketch some curves. Some surfaces. So, for instance, let's do r of uv is equal to 2 cosine of uv, 2 sine of u. What was that middle term? Oh, it's just y. It's just a v, and this is just cosine of u, and this is just sine of u. It could still be a sine of uv, where we set v equal to 0 for all values. So our x is equal to cosine of u, or 2 cosine of u. Our y is equal to a v, and our z is equal to a sine of u. You see how this is a r of uv? Because this vector is defined in terms of the parameter u and the parameter v simultaneously. It does not require that each I, j, and k component have both u and v in it. All that means when this is r of uv means I can only express r if I express it in terms of the parameter u and v altogether. So notice our x is equal to 2 cosine of u. Our y is equal to v. Our z is equal to 2 sine of u. This just begs us to do something. These two terms just are begging us to do something when there's a sine and a cosine together. It's just begging us to apply the Pythagorean identity. The Pythagorean identity, sine squared u plus cosine squared u is equal to 1, can be utilized if we square these guys. X squared plus z squared is equivalent to 2 cosine of u quantity squared plus 2 sine of u quantity squared. Okay, this breaks down to the squares distribute to each of the terms in the product, giving me 4 cosine squared u plus 4 sine squared u. Notice that I can factor out the 4. So I get a 4 times the quantity cosine squared u plus sine squared u. Okay. The Pythagorean identity implies that what's inside the parentheses is equal to what? Very good, Jamie. That equals a 1. So this whole thing equals a 4. But that equals this. So we get this equation. What does this remind you of? A what? Circle. Oh, but I thought circles were only like x squared plus y squared. Oh, what do you mean it's just around the y-axis?
Like that's where instead of being centered around the z-axis. Maybe it's a cylinder.
By centered, do you mean symmetric?
I think so.
Okay. So like x squared plus y squared is equal to 4, for instance. X squared plus y squared is equal to 4. That's still centered at the origin, okay? But its axis of symmetry is the z-axis, because the z is not apparent in the equation. So now we go to x squared plus z squared. Now it's like this. Its axis of symmetry is the what axis? That's what you're talking about. It's the y-axis. That's the axis of symmetry. Did you have a question or a statement?
I was going to say, so then is it a cylinder? Why is like free? Or like stretches or no?
Oh, well, y is v, right? And what is v? Starts with a p. V is a parameter. And can v, if v is a parameter, what can v be? If v is a undisclosed parameter, then what can it be? Any real number. So it's a free parameter. So as you suggested, that should generate a cylinder. But if we have fixed it to equal a specific value, then it would just be a circle at that specific value.
It's like a cross-section.
Cross-section of the cylinder. That's right. But because it's unspecified and it's free, this forms a cylinder of radius what?
Yeah.
A cylinder of radius 2. So now we've generated a parametric surface. So once we create this parametric surface, we kind of got to check what our parameters can range. We've already discussed what the V parameter can range. V can be what? Anything. Anything, even real numbers. But what are the limits of U based off of how we define things?
-1 to 1.
You're on the right track. You're talking about what is the output for sine and cosine. You said -1 to 1. That is the range of the sine and the cosine function on the unit circle, right? But we're asking, what is U? And U is an input, not an output. So what inputs could possibly give me this output when evaluated in the sine and cosine trigonometric functions? 0 to 2 pi. Okay, well, 0 to 2 pi would get you, here's my 0, here's my -1, here's my +1. 0, oh, did you say 0 to 2 pi?
Yeah.
Okay, I thought you said 0 to pi over 2. 0 to 2 pi. 0 to 2 pi, for both of them, will give you this whole output, yes. So your book then goes on to talk about, but what if we do restrict? So, matter of fact, 0 to 2 pi would give you this, but 2 pi to 4 pi could also give you that, and 4 pi to 6 pi can also give you that, right? The book then states that, well, now that we have this cylindrical surface, what kind of like restrictions, what kind of modifications would a restriction on the parameter of U give us? So as you stated that, yeah, 0 to 2 pi works and whatnot, that's a valid interval. What if we were to like restrict that interval? Let's say, I want to say U between pi over 2 and 0. How does that change the surface? They also say also restrict V. V like so. How does this change our surface here? So V is no longer free. And V tells us just kind of the height of the cylinder, right? So the cylinder will now range from right here, right, all the way to right here at 3. Y is equal to 3. And we chop it off. So the rest of the cylinder gets deleted. That's the action of doing this. What's the action of doing this? Because it was going from 0 to 2 pi. What's the action of doing that? Notice that only sine and cosine care about U, so it's going to do something to them.
Instead of a circle, is it going to be like a fourth of the cylinder? So you
Oh.
half it, and one piece is what that is?
Yeah, that's totally right. Completely right. It's the first piece of the rotation. Basically, the first quadrant of rotation. Yeah, it's completely right. So, how to draw this? There you go. I've drawn it. Maple will draw it better for you. Good old Maple. Maple. Okay. Okay. Then it talks about use a computer algebra system to graph stuff. You guys can do that stuff in lab. Okay. One of these is, it has like some, wow, it's a really cool picture though. I'll just talk about it and talk about the picture. I'll just write it down and talk about the picture that it generates. Because at this point, you guys know how to use Maple, right?
Yeah.
Maybe you guys could show me how to use Maple. I forgot how to use Maple. It's been a very long time. The R of U is equal to, what does it say? 2 plus sine of V times cosine of U. Plus 2 quantity, 2 plus sine of V sine of U. Plus a cosine of V. Interestingly enough, when you graph this, you get like a corkscrew looking thing. Okay. So then it talks about which grid curves have U constant, which grid curves have V constant. You could read about grid curves and look at that stuff. Because I don't do Maple stuff, I'm going to move on. But that's just cool how a parametric curve in one variable, like the helix, because this looks like a three-dimensional helix. Compare this equation to our prototypical favorite parameterization, the three-dimensional helix, just a helix. Notice that there's some similarities there, but whenever you go from here to here, from here to here, this is a curve, and this becomes a surface. That's like one of the main points of this section. So now let's talk about parametric equations for a plane. So we already know how to do equations of a plane. But here's another way to do it. So here's some point P. Okay. Let's say we have a vector A and a vector B pointing out of this. Here's a vector A. Here's a vector B. Okay, and there's a point P. And we're starting at some initial point P naught. Okay. So we can construct mathematics that will allow us to create some type of plane. Right now, it doesn't look so hot, right? Because it's like, well, how can I create a plane? It wouldn't even encompass this whole situation. Fear not. Oh, fledgling mathematicians, fear not. Because we can scale vectors, right? I can scale this vector by CA, some constant. And I can scale this vector by another constant. Let's stay consistent here. Oh, C is a constant, but U is also a constant. We'll just keep it consistent. We can call this UA. And we can call this VB, where U and V are scalars. They're parameters, which means they're scalars. They're just real numbers. Okay. Once we do that, we attain a parallelogram shape. or, you know, it's supposed to look like a parallelogram shape. Either way, it looks like an enclosed shape at the tips of the vectors. So let's see how we can define a plane like this using two parameters. Okay. So let's analyze what our displacement vector is. How would I determine what my displacement vector is? That P naught to P. How can I quantify that? Notice that one interesting thing about this problem is it seems like it's in 2 dimensions, and the way it's constructed in the text, it actually is in 2 dimensions. But notice that it doesn't specify whether P naught is an origin. Typically it is. But in this situation, the book doesn't assume that that's necessarily the origin. We used to treat that original point as the origin. But it's not necessarily the origin at all times. We don't have to have that be like that. That's just how we were doing it for convenience initially, but we don't have to do that. All that it requires to not deal, all that it will require to not have to deal with that is here's our origin now denoted by O. Here's still some P naught. We can say that some vector R that points to the same spot that we are pointing over here. Okay? And now it's not just R of T, we want R of U of V. Right? Before we had an R of T, but now we want an R of U V. And it makes sense because this R is going to create a plane, a 2-dimensional surface. So how can I construct this R of U of V? Using vector addition. Well, first, one way actually I could draw it better. Let's see if this will work. Actually. Nope. There we go. R of UV. So you can see it better. One way that will work is we can say, okay, well, R of U of V is just the displacement vector from the origin to P naught plus the displacement vector from P naught to P. This would be my R of U of V. And that kind of like makes it more suggestive to look that way. Okay, but what is that in vector addition? It's just your R naught plus your vector addition of your UA plus your vector addition of your VB. Well, what is R naught? R naught is this right here. R naught was always defined as this thing. This was always defined as R naught. The origin to your initial point, the displacement vector from your origin to your initial point was always defined as R naught. You guys remember that from test 1 material. Okay, so here's a cool thing. Now we have a new representation for a plane, a vector representation for a plane. It has a R naught, it has a UA, and it has a VB. Okay. And as before, our R, X, Y, our R naught, there's some X naught, Y naught, Z naught. What else do we have to list? So then we can say let A be arbitrary and defined like so, and let B be arbitrary and defined like so. Okay. Then what does this break down to? Namely, mostly this. What does this break down to? Well, it breaks down to, and I think I don't need this picture anymore. But picture breaks down to this thing. That's a V3. When you add them all together, I get x naught plus UA1 plus BB1, y naught plus UA2 plus BB2, z naught plus UA3 plus BB3. So take a look. This all equal my R, which was my x, y, z. So each component gives me x is equal to my x naught plus UA1 plus BB1. Y is equal to my y naught plus UA2 plus BB2. And z is equal to my z naught plus UA3 plus BB3. So before, we had parametric equations in the variable t. Now we again have parametric equations in the variables u and v, respectively. So know that this is the generalized form, and know how to apply it for concrete examples. So R of u v is equal to R naught plus UA plus VB generated these equations here. And I know what you're thinking. I thought you said this was only a two-dimensional situation. Why is there an X, a Y, and a Z? Am I lying? No, it still describes a two-dimensional surface. The two-dimensional surface is just embedded in 3 dimensions. Cuts the circle into a quarter. Yes, that's right. The XZ plane. Yes, I should have been looking at you guys. You're right about those in the past. Oh yeah, but this is just a consequence of the fact that I need Z components, Y components, and X components to locate it in 3 dimensions. It's still a 2-dimensional entity, but I need all those values to parameterize it. So, ooh, this will be fun. Let's parameterize a sphere.
When you say 2 dimensions and 3 dimensions, is that like you have 2 dimensions and some line or some curve? Instead of putting it on a 2 dimension, you put it in a box. It's the same line or the same curve or whatever.
Right. It's like a piece of paper.
But it has like no like depth or whatever. Just be a line in a box.
Yes.
Yeah.
The line could be on a piece of paper, or the line could be in a box.
Yeah.
It's still a line. It's just living in a different location in each of those different situations. Here, it's still a two-dimensional surface. It's just living in 3D, so we have to like give it three-dimensional coordinates. It could have also lived in 2D, and we wouldn't have needed to give it three-dimensional coordinates.
Would you have to project it then?
I mean, you could. It wouldn't be the same surface unless the surface was perfectly flat. If it was perfectly flat, hovering over one of the planes, either the XY plane, the YZ plane, you know, and then you project it, you get the equivalent projection of what you had before. But not always. What if it's curved? Like, what if it's slanted?
Yeah.
If you slant it enough and project it, it seems like just a little tiny thing. Like the shadow that it would cast would just be a little tiny thing. But really, it's a huge plane that you just can't, the projection makes you lose that information. Unless you have the inverse map. Let us parameterize a sphere. Of radius A. Okay. Trying to draw the best sphere I've ever drawn in my life. Okay, let's go. Not bad. X, Y, Z. And so let's take some like cross sections of this sphere. And we'll help to do in different colors. Cross section. So notice that how much the angle varies about the XY plane is our how much the angle varies with respect to the XY plane, right? That's our phi. And how much that angle varies between the Z axis is our theta. So if I make this cross section right here, this is when phi is equal to some constant c. It is the line of constant phi. It is a line of constant phi. And we can have a line of constant theta. Like from right here. This should be a line of some constant theta equal to a k. Where if I change theta, that would change the cross section. So let's see how this is going to help us parameterize the sphere. Okay, nothing new from them. Okay. So recall beautifully from spherical coordinates what the transformation equation from rectangular to spherical was. Oh, by the way, did you guys enjoy that question that asked you to go from cylindrical to spherical? Many of you seem like you enjoyed it. There is no equation that takes you directly. You need to go from cylindrical to rectangular, and from rectangular to spherical. There isn't. You are not presented any equations that lets you go directly. But that's the part that challenges you. So the transformation equations in X, Y, and Z were so. It was, actually know this one, rho sine of phi cosine of theta, rho sine of phi sine theta, and this last one was rho cosine of phi. Am I right? Am I wrong? Right, because when we had like that. But in this equation here in this world, it's set equal to a squared, not rho squared. So all I got to do is change these to some a's. Doesn't really change the mathematics at all. Just changes what it looks like. Now, here comes the fun part. How do we parameterize it in two parameters? we realize what is the definition of a sphere. What makes a sphere so special? It's the set of points in three-dimensional space that are equidistant to some fixed point, its center. Okay. So if spherical coordinates, here's my x, y, z in rectangular. Spherical coordinates goes to some rho, which is our A. Rho theta phi, right? But our rho is constant. Our rho is a constant. Or else this is a dynamic sphere that's moving and it's getting bigger and smaller at the same, our rho is constant, our A is constant. When we try and create a parametrization of the sphere, I don't have to really worry about what A is doing. All I have to worry about is what theta and phi is doing. Theta and phi are our two parameters now. They allow us to now parameterize the sphere. And guess what the parameterizations will be? So I can parameterize my sphere as a, oh, I need some space here. Maybe I can fit it in, yeah. No, I don't, not this. Won't be able to fit it in. Delete that beautiful picture. Our parameterization, our R of U, V, will just merely be the transformations into spherical coordinates. But now we don't have to use U and V. Those are arbitrary parameters. I can use theta and phi. So just place our transformation here. A sine phi cosine of theta. A sine phi sine theta. And for z, it transforms as A cosine of the angle phi. And there you go. We create a parametric equation in two variables of the sphere. And it's as easy as the spherical transformation. And the spherical transformation is as easy as the application of Pythagorean theorem twice. I've still not made those YouTube videos. I only sleep about 4 hours a day ever since 2020 started. So yeah, I've not been able to get to that, but I will. I will eventually get to that. I know you guys are dying to see it, or you've probably done it for yourselves already. So now we have to discuss what phi and theta range through. What values do they range through? Trying to go directly causes several illogical statements like 0 equals 1 and such. Caleb is referencing going from cylindrical coordinates to spherical coordinates directly. Yeah, I told you don't do it, bro. I said you need to go to rectangular first. He was at the end of some class trying to discover an equation that goes from cylindrical to spherical directly. As you guys notice, things that get discussed in class sometimes appear on quizzes and tests. Like Ivor was talking about cones. So I thought to put a cone on the test. So if you guys talk about something in class, remember it. Don't let it fly out of your brain, because if I say something in class, it could definitely be something that I find really cool and interesting, and that might pop up on an exam. So we have parameterized it in theta and phi. We got to think about what does theta and phi range. That's a very easy way to, oh no. It's a very easy way to understand what theta and phi range. Very easy. All you got to do is this. What am I doing? That's a horrible, that's an ellipse. It's an ellipsoid. Okay, come on. There we go. So then, from here down to here, versus all the way around. What's the orange? What's the red? Theta or phi?
Orange is phi.
Yes.
Red is theta.
Yes. So what is that ranging from? What values do these parameters range from? Namely, what does theta range from? What does phi range from? Phi goes around in a whole circle, so 0 to what? A half. Theta only goes from one end of the z-axis to the other end of the z-axis. So 0 to what? Haha! Very good. I believe we're out of time here. Then we got one more minute. See if I can say any more things. Oh. I'm such a physicist. I've mixed up theta and phi. Here your book is saying phi ranges from 0 to pi, and that theta ranges from 0 to 2 pi. But based off of this diagram, it doesn't seem like that. So well, r theta and phi, physicists and mathematicians tend to switch their thetas and phis. One is supposed to describe the angle between the z-axis, so it has to range 180 degrees or 0 to pi. The other one talks about what is the angle about the xy plane, and that's what I thought was theta.
Does it matter since we've been keeping it consistent?
No, if you keep it consistent, it doesn't matter. Actually, according to this picture, phi is going around the circle, it should go to 2 pi. According to this picture, theta is going from the z to z, so it should be 0 to pi. That's how their picture looks like, but they have different values. So we parameterize a sphere. After that, what we didn't get to is parameterizing a cylinder, and then parameterizing a cone. But those are very intuitive based off of what we've done before. Very intuitive. A cylinder is just a circle that has a free parameter in one of the x, y's, or z's. The elliptic paraboloid, again, it's the generalized sphere. And the cone is like the test problem where you have z squared is equal to something, or you could take the square root of both sides and get z is equal to plus or minus the square root of that stuff. That would be the dual cone, one going up, one going down. Many of you caught that question in its tracks.